afternoon, depending on where you are. And I'd like to jump right into this, assuming there we go. Okay, so what we're trying to do is sustain reservoir capacity against the challenge which is posed by sedimentation. To have a sustainable management of reservoirs, we need to minimize the rate of volume loss. We need to try and bring sediment inflow and outflow into balance insofar as possible, instead of just having reservoirs that simply trap sediment. And we want to sustain long-term storage or other benefits. Some benefits are intimately related to storage, and others are a little bit more loosely related. And we want to minimize environmental harm. Now, Tim mentioned that I would start with going over monitoring, and a couple days ago we decided that monitoring is sufficiently important that we would have a separate webinar on monitoring and analysis of sediment. So I'm going to get right into the topics of a brief discussion of how the sediment processes work and why it's important to reservoirs and what we can do. Now, the first thing you need to understand, these are storage yield curve. We have the yield of the reservoir versus live storage, and these are pretty typical for water supply reservoirs. You have a curve that corresponds to a given level of reliability, and another curve which has less yield for the same amount of volume, which is, in other words, if you have a higher percentage of reliability, you will have less yield, and you have a lower percentage of reliability, you have a higher yield, but your reliability is down. And what happens when you have sedimentation is you move along a curve. For instance, if you have a 95% reliability and you lose storage, your yield over here is going to drop. On the other hand, if you maintain the same yield, you're going to go from the 95% to the 90% curve, so your reliability drops, or you're going to lose some combination of the two. Now, we have a climate change issue, which one of the primary concerns of climate change is that it's going to cause more intense droughts and floods. And this will reduce the effectiveness of existing storage. Basically, what's happening is that the storage yield curve is shifting, and it's shifting downward. You see this, the 90% curve from today is shifted down to less yield for the same amount of storage at some point in the future. So we need more storage to achieve the same benefit. But this is occurring at the same time that we're losing storage to sedimentation. So we have the problem of not only we losing storage, but the sediment problem is accelerating the problems posed by climate change. Now, in the hydropower sector, the story is a little bit different because turbines are usually sized to process a substantial flow. So in a hydropower reservoir that's operated for storage, your total annual energy doesn't change that much as your live volume change. Now, I've run these analysis for wet climate reservoirs, humid zones, South America. This particular one is for a monsoon climate in Nepal. It's a storage reservoir. And you can see that even though the total annual energy doesn't reduce very much, your dry season energy and your firm power or your firm energy is reduced dramatically. So you need to be a little bit conscious of the different variations and impacts that accompany sedimentation. Another impact is, of course, damage to equipment. This is a needle valve out of a plant in South America that was subjected to a very severe drawdown. They dropped sediment into the turbines, and this damage occurred in less than 24 hours. So sediment, particularly the sandy sediment that you see in river deltas, reservoir deltas, you need to keep those away from your equipment. And finally, what is the end of life scenario? Where is the reservoir going to end up? This particular example is from Venezuela, the Camaré or Pedregal Reservoir. It has two different names. I visited there in 1996. It was only 14 years old and was already full of sediment. The little river you see here on the left side of the screen is actually just going over the spillway. And this is what you'll find on Google Earth today. The dam, it's an earthen dam, it's completely, it's failed, and all the sediment is coming out of the watershed. You see the slump failures inside the reservoir. So this is the type of future that can happen if we don't do something with sediment. The reservoirs in the United States and most areas of the world have traditionally been designed using the concept or the paradigm of a design life. Under design life, you're looking at a 50 or 100-year design, and you design a sedimentation pool for that capacity. You don't really worry about what happens later. That's someone else's problem. You assume it'll be decommissioned. It's not the designer's problem. But we have a lot of reservoirs today that are reaching their original quote-unquote planned obsolescence age, but they're no less useful. In fact, we are more dependent than ever on these reservoirs. So we have to face the problem of how do we take a traditional design approach and perform a sustainability intervention. This is feasible. We've done it at a number of sites already, and this is where we're going to have to go on any reservoir that you want to sustain for long time utilization. With a new project, you can start from scratch with a sustainable design. Not too many reservoirs coming up in the United States, but this is an issue in some of the other developing areas of the world where a number of new reservoirs are under construction. So the storage loss process, we need to manage the sedimentation, we have to understand the processes that are involved. We need quantitative information for monitoring, and and that information is necessary to plan, to execute, and to optimize the management activities once they've been implemented. And as I had mentioned, we're going to have another webinar which is strictly looking at these topics. One other thing you need to really keep in mind is sediment transport is highly variable in both time and space. This makes it difficult to monitor. Your concentration of sediment may vary over 3 orders of magnitude easily within a river. The discharge may vary over 2 or 3 orders of magnitude. So this gives you perhaps 6 or 7 orders of magnitude of change in the rate of sediment transport in a given stream. And of course, the big sediment transport events are the big storms. But those also provide specific opportunities for management, as we will discuss. This rather busy figure gives you basically the management options that are available. They're classed into 4 different types of strategies. We can reduce the sediment yield. We can take reservoirs and manage them to route the sediment through or around the reservoir so that sediment doesn't collect. Or once the sediment has been deposited, we can remove it from the reservoir. Or the 4th one, we have a number of adaptive strategies. These adaptive strategies do not actually remove sediment or don't achieve a sediment balance, but they help adapt to or delay the consequences of sedimentation. And I also put monitoring over here at the bottom right corner because that is so essential, not only in the planning, but also to optimize the execution of any of these activities. So let's start with looking at reduction of sediment yield. We can either reduce the sediment production or we can build a large sediment trapping reservoir above the one we already have. In the United States, there are lots of reservoirs. So we are looking at yields entering our reservoirs from only a limited portion of our total tributary area in many river basins. But as the upstream reservoirs become sedimented or start to pass sediment through, the sediment yield may increase over time. But let's look real quickly at sediment reduction. The sediment yield problem starts with erosion. Raindrop impinging upon bare soil or unprotected soil, and you get an active initiation of the erosive process. This photo on the right just shows very briefly, this is from a road fill. This is a loose soil that had some gravel in it, but you can see how everywhere that the soil is protected, the erosion doesn't occur. Just a dramatic example of the importance of protecting soil against erosion. We don't realize it today, but because we have in the United States a very well implemented erosion control program, but it didn't used to be like this. Photo on the upper left, the 1930s, this is the driftless region, Minnesota, but this is typical of many, many areas throughout the country once upon a time. And through a variety of techniques, contour planting, for instance, no-till farming, this problem has been in large part greatly reduced in the United States, but many parts of the world, it's not there yet. Some areas, the soils are degrading, actively degrading, as land use becomes more intense. These data, though, from the U.S. Army Corps of Engineers, these are from Midwestern reservoirs, Kansas, Oklahoma, and mainstream Missouri, the dotted red lines. And these show basically from the 1950s onward that there's been, in most sites, a trend of decreasing rate of sedimentation in reservoirs. Why? We don't know exactly, but it's probably reduction of sediment yield over time. Sediment consolidation over time may be another factor. It's probably not due to changes in survey methodology or reduction of trap efficiency, given the size of the reservoirs at present. But it does show that the impact that soil conservation can have, but it also, you need to remember that soil conservation is a long-term process. You don't go out, treat a watershed, and see the results tomorrow. Another factor to remember is that the erosion rates are highest and your sediment transport rates are extremely high during large storms. Here we're looking at about 15 years of data from the Susquehanna River, Conowingo Reservoir. It's just north of Washington, D.C. And it shows you the impact of Tropical Storm Lee in terms of discharge. These are the events that really have a big impact. Here's some more data. This is on the left-hand side, I've got Rio Valenciano from here in Puerto Rico, and you'll see the effect of Hurricane Hortense, which came, it was very wet hurricane, didn't have a lot of wind, but it's very wet. And you can see that the one-day sediment yield was about equivalent to about several years of normal precipitation. Here's another example, this one over from California, the Santa Ana River, Southern California, and you'll see again a very large event accounted for most of the sediment yield over this 8-year period. I don't have the graph here, but we have one of the reservoirs in Puerto Rico, Caonillas, had a sediment yield, or it lost as much capacity in one day due to the passage of Hurricane Georges back in 1998, as much storage loss in one day as occurred in the first 50 years of reservoir lifetime. Here's an example from Nepal, Kalakuni Reservoir just outside of Kathmandu. Gradual decline capacity, big event, a very wet monsoon, the watershed came apart, a lot of sediment came out. The red line shows the sediment yield, and then it tapers off again. So these big events can have a very big impact, and you need to be aware of them. Now, with respect to the spatial distribution of sedimentation, about 70% of the worldwide sediment yield comes from less than 10% of the watershed area. Now, this same kind of relationship occurs at all watershed scales. You give me any watershed, and you look in detail at where the sediment come from, and you'll find that there is a small percentage of watershed that accounts for most of the sediment. So to have effective control, you need to focus on erosion hotspots. And again, going back to the theme of the extreme events, just because you see an area that looks green, it looks stable, doesn't necessarily mean it is. This is an example from Colombia, and you see here at the bottom a powerhouse and a small little stream. But you look at the stream and you'll see that there's these big boulders in this stream which aren't transported by normal events. There was a large event in the 90s, a very intense storm. The watershed basically became unraveled. And look at the grain size inside the powerhouse. Debris flow, a lot of damage. These events happen. I perhaps see a lot more than most people do, but you need to be cognizant of these types of transport events. And finally, if you're going to make structural controls for sediment yield, you have to consider that, will that structural control stay in place? Gabions, totally inappropriate for use in any type of a river system. This is in South America, but if you see gabions installed anywhere in the world, this is eventually where they'll end up. But concrete also doesn't work when they get cut around the sides or they get undermined. So look at producing vegetation in your watershed, because that's what will give you self-sustaining control. So basically for watershed management, you need to look at getting the support and implementation by the users in the watershed, and they may number in the thousands. Decades of effort may be required to achieve measurable reduction in sediment downstream, and the project success is not under control of the dam owner. So you can't be assured of a timetable. If you have a sedimentation problem, typically you're not going to be able to say, well, we're going to do watershed management and it's going to solve the problem. Now, if you are implementing watershed management, ensure that the efforts are focused on the high yield sources, that there's a realistic potential to achieve a substantial level of control, and that there will be long-term community support after any special project funding ends. If you focus on improving community or farmer income through better soil management, that is self-sustaining. So I don't want to say something bad about watershed management. It's an essential and key element of this process, but in the United States, it has been very successful to date, but we need to move now to the next level. Sedimentation patterns. Within the reservoir, you can basically break the sediment deposits into two groups. We will call the upstream group the delta, which has a top set or a top slope and then a foreset. And then everything else downstream of the delta is fine sediment deposits. And these sediments will many times be transported by turbid density currents. And the turbid density current will flow to the dam. It will cause a muddy lake, a submerged muddy lake to be created. So you have clear water, muddy water, which is heavier, more dense than the overlying water. And then you have sediment deposits. And these muddy lake will cause horizontal deposits to be created. So basically you have a sandy, coarser material in the delta, and depending on where you are, it may be gravels and cobbles, it may be sand, it may be coarse silt. And then your finer material closer to the dam. So now let's route these sediments that are inflowing around or through the reservoir. A couple of procedures we can use. We can bypass the sediment. We can bypass around the storage pool by putting the storage pool off stream or by using a bypass tunnel. Or we can pass the sediment through the reservoir by venting the turbid density currents that we just saw, or by washing the sediments through the reservoir during large events by drawdown sluicing. So the bypass operations, they're basically two types. You can use an intake to divert water into an off-stream reservoir. The flood that contains all the sediment load will go past the intake on downstream, does not enter the reservoir. The option of the bypass tunnel is to create a tunnel or a channel to bypass floods. The bypass tunnels are typically rather large and costly. So there are more than a dozen or so reservoirs in the world which use a bypass around an on-stream structure. The off-stream structures are typically more feasible. This is an example of an off-stream reservoir here in Puerto Rico, one of two that we've built here. This one you see has the intake on the Rio Blanco. It has a 66-inch pipeline, goes to the reservoir, and the reservoir collects primarily water during moderate flows. We had a Hurricane Maria that came through about 5 months ago. And we didn't have to worry about sediment in this reservoir because hurricane flood is not going to pass through a 66-inch pipe. Off-stream reservoirs can also be used in series. They can be used for hydropower operations. This is the example of the Czech project in Colombia. And I apologize, we're having electrical problems still here in Puerto Rico. I am a little bit in the dark, but we seem to be continuing to operate okay. Now, an off-stream reservoir, this is the San Francisco Reservoir downstream here. The next photo shows this reservoir being dredged after about 40 years of operation. An off-stream reservoir does not have zero sedimentation, but its sedimentation rate will be greatly reduced as compared to a normal on-stream reservoir. For instance, the Rio Blanco Reservoir that I showed you the picture of a couple of minutes ago, that reservoir is expected to have a half-life, the time required to lose half of its capacity, on the order of 1,000 years or more. And the dredging volume will be, at that time, on the order of 2 million cubic meters. We don't need to have a large storage capacity for sediment storage in off-stream reservoir, and that makes them more economical. And we also don't need a large spillway. Power's back on. Next topic, turbidity currents. We saw previously that a turbidity current enters a reservoir, plunges, runs along the bottom, and creates a muddy lake. And that muddy lake, the water can be released to reduce the amount of sediment that is retained in the reservoir. Here is a photograph of Nurik Reservoir in Tajikistan. And this is the turbid water entering, and this is the plunge point. This is at this point right here. You have downstream flowing water, and this plunging water will also create a countercurrent, a local countercurrent. So if the reservoir is carrying any debris or logs downstream, you will have a collection of debris at that point. This didn't have debris, but you can see very clearly the reservoir between the clear water and the dark water, sediment-laden water on the right-hand side, flowing from the right towards the left and plunging to the bottom of this reservoir, and it will go now for another 30 kilometers down to the dam. This is a reservoir in South America showing the pattern of deposition that you get from density current deposits. Remember, we said that you had a muddy lake that created these horizontal deposits. Notice that the power intake is a higher elevation, so the density currents are not being released. They're just collecting in the form of a muddy lake. And we have accumulated here more than 50 meters of sediment. So to release a turbidity current, the turbid current must already exist, and it needs to be transporting sediment to the dam. This does not always happen. You need to have an outlet structure placed so that the turbidity current can be released instead of being trapped and sedimenting. And the efficiency of this will typically decrease over time as the reservoir fills with sediment, which I'll show you in a second why that happens. The turbidity current can be released through a low-level outlet, turbidity siphons, or through power turbines. It does not require reservoir drawdown because you do not have to draw down the reservoir. It's a method which can be used without interfering with your normal operational regime on the reservoir. And its applicability typically is the first method that you can use when the reservoir is brand new, and its efficiency will vary depending on the reservoir. In some Chinese reservoirs, ideal situations, they've been able to discharge about 50% of the sediment load through turbidity currents. Here's a photograph of a small hydropower reservoir in Puerto Rico. This is Dos Bocas showing the turbidity current coming into the reservoir, running along the length of the reservoir and being released through the turbine. See the water that's orange downstream of the dam? So these do happen. It is a real phenomena, and they can help reduce the rate of sedimentation. The problem with retaining turbidity currents is that if you keep that fine sediment in the reservoir, the delta sediments can prograde on top of them and reach the dam faster. These fine sediments, you can typically run them through a turbine without excessive damage. Now, you don't have to use a bottom outlet. You can also use a siphon type of device, which does not have to be hydrostatically sealed, to siphon water from lower levels up through a higher level outlet. You could even run it over the spillway. Here's an example from Taiwan. They call it an elephant trunk intake, where they have constructed this type of intake to siphon turbidity currents from their reservoir and release them downstream during typhoons. Taiwan has very weak geology. They have severe sedimentation issues, particularly during typhoons. Now, over time, the turbidity current will change the geometry of the reservoir. Initially, the turbidity current can flow down the channel occupied by the river. And you'll see you have a nice compact current. But as this begins to fill with sediment, because the turbidity current will deposit sediment along its route, it will eventually become flat bottomed, which is a typical sedimentation pattern that you'll see in a reservoir. It will transition, the channel will fill in first because the turbidity currents will fill that in first. And as it fills in, their turbidity current no longer has a channel to run down, but it now spreads out and is flat. You have friction at the top, you have friction at the bottom, and also at the top you have the exchange between the turbid water and the clear water, so the turbidity current becomes increasingly diluted. And by these combination of factors, you may lose the ability to transport turbid water to the dam, unless you have flushing of the reservoir, which will reopen this channel through a flushing procedure. Elephant Butte Reservoir had, on the Rio Grande, had a turbidity currents would reach the dam when it was originally constructed. But by the 1950s, they were no longer reaching the dam because your geometry changes over time and it works against the movement of turbidity currents. And because of this, if you are releasing turbidity currents initially to help reduce your sedimentation rate, you have to think that in the future, this is not going to continue forever, and that at some future time, you may have some other type of sediment management process or activity that you'll have to conduct. So when you start planning on sediment management, don't think about what you're going to do just today, but also what you're going to be doing in 50 or 100 years in the future, so that whatever you do today ties into or helps the future management activity. The next thing I'd like to talk briefly about is drawdown looting or sluicing. Basically, what you're doing is you're reducing the detention time to reduce sedimentation. You want to sustain a high velocity through the reservoir to keep the sediment moving, and you want to minimize deposition. So you do this operationally by holding the reservoir at a low level during an individual flood or during a flood season. And it requires management of high sediment concentrations in the water that is going to be diverted out of your intake. If you're only going to draw the reservoir down for an individual flood event for a few hours or half a day, maybe you can turn your water supply system off for half a day. But if you're going to be drawing down for 3 months, you have to deal with that sediment-laden water that's going to be passing through the reservoir. Applicability, it'll work on reservoirs of all sizes. The efficiency varies considerably depending on the reservoir, the geometry, or hydrology, but it does require large capacity gates because you have to pass flood flows through the reservoir. This graphic shows you conceptually passing a flood, maintaining the reservoir at a high level versus passing the same flood at a high velocity with a reservoir at a low level. In the top graph, you'll see you're going to be trapping sediment, and the bottom one, you'll be passing sediment through the reservoir. This is an example of a seasonal drawdown. This is Kali Gandaki. This is in Nepal, monsoon season. This is, in the foreground here is the desander, and over here on the right side is the dam. This photo is taken during the dry season, during the winter months. The reservoir is at a high level, and they're maintaining 3.5 million cubic meters of capacity for daily regulation for hydropower. Now, the interesting point about this reservoir is that by this procedure, they have been able to maintain this 3.5 million cubic meters of capacity since the dam was built in 2002, even though the annual sand load is double this capacity. Sand load here runs 6 to 10 million cubic meters a year, but they're able to maintain it. How do they do it? Here's your Monsoon Hydrograph. The black line shows the discharge of water. The blue line up on top shows you the water level in the reservoir. During the dry season, the water level is to maintain high. The wet season comes, as soon as you get more than 300 meters a second of flow, you drop the level in the reservoir. You generate a high flow velocity, you maintain low water level, high flow velocity during the monsoon. At the end of the monsoon, you drop back below 300 meters a second, water level goes back up, and you're operating back in your wintertime pondage or power peaking mode. And you see down below in the graph, while you're impounding water, the sediment reaching the turbines, which is the green line, is very low, and the red line shows the sediment concentration in the river, sand concentration, not total sediment, sand. And as soon as you drop the level, your concentration jumps. And it's high throughout the entire monsoon season, and then it drops as soon as you raise the water level again. And that's why you have the desander we saw in this picture here. This desander is only used for 3 months of the year. The rest of the year you don't use it because the reservoir is trapping all the sediment. And there's not much sediment being generated anyway. This river produces about 95% of the total sediment yield during the monsoon season. Now, for individual storms, for instance, this is a reservoir in Puerto Rico where we have worked up a scheme of this type. You start your normal operation, you have real-time hydrology, and you're determining how much water you have in the watershed, how much water is in the reservoir. A large event is coming, like a hurricane. You start to open the gates, you lower your storage, but your sum of storage in the reservoir and in the watershed is always sufficient to refill the reservoir. The gates fully open during a peak of the storm. Your 24-hour from the watershed exceeds the reservoir capacity. You're sluicing water through the reservoir, possibly even scouring some previously deposited sediment. The storm ends, you close the gates, refill the reservoir. Very important for areas that have very intense events. We've had events that had enough water to fill this reservoir 10 times within 24 hours. So this is an appropriate management strategy for this particular site. Third, remove sediment. Now, for sediment removal, we have two basic types of options. We can do mechanical excavation. We can either dry the reservoir up and use mechanical equipment, as you might manage a debris basin, for instance, or you can use hydraulic dredging. Dredging refers to any activity removing sediment from underwater. The other option is hydraulic scour using flushing. Now notice that hydraulic flushing, obviously you're going to flush the sediment downstream, and dredging, you may also be placing sediment downstream. And under both of these strategies, there may be the need to flush the river below the dam to mobilize those sediments that were released downstream. Pressure flushing is when you open a low-level outlet and the reservoir is maintained at a high level, and you generate a small flushing cone. This is very localized, only in the immediate vicinity of the outlet. This picture shows a photograph of a reservoir in Brazil, mostly sandy sediments. You see the intake here on the left-hand side, and you see the semicircle, which is the scour hole, which has been created by the pressure flushing procedure. You can see it's very, very localized. This is all you're going to get from pressure flushing. You can keep an intake open if the pressure flushing outlet is underneath an intake, for instance, but that's all you're going to get. Removal by dredging. Dredging is a well-developed technology. You can exactly control the amount of sediment that's removed. You can scale it to any size using multiple dredges, and you use a relatively small amount of water. It doesn't require the reservoir operation to be modified. For instance, you don't have to empty the reservoir. You can continuously produce power, for instance. The sediment does not have to go downstream as it would with flushing. You can transport it as far as your money will take you. The slurry pipeline is a nice, clean way to transport sediment. You don't have all these trucks running up and down highways, thousands of trucks potentially. And hydropower dams, you can use electric dredge and self-supplied, presumably cheaper power. And it is also a method of last resort. When everything else doesn't work, hasn't worked, or wasn't done, it may be feasible to dredge. Now, this photograph shows the dredging at the Baja and Chicaya project in Colombia, which is the longest continuous dredging project that I know of anywhere in the world. They've been dredging continuously since 1962. There's two types of dredges. There's a Sawyerman, which is like a skyline type fixed drag line. Use this to pick out the cobbles coming in from the delta. And then they have a conventional cutterhead dredge. Both of them discharge into a tunnel, which discharges right below the dam. It runs about 15 kilometers down a very narrow canyon, and then discharges onto the Pacific coastal plain. Conventional dredges, conventional cutterhead dredge, typically with a ladder pump. But if your reservoir is very deep, you can also get deep digging dredges that'll dredge over 50 meters deep. These are typically used in Europe for sand and gravel mining operations. You can also, in some instances, use a siphon dredge or a hydrosuction dredge, which is a dredge which uses the water level differences between the water in the dam and the downstream face of the dam, using this head to run the water, push the slurry through the pipeline and below the dam. Because you don't have a pump in the dredge and you don't have booster pumps, you're typically limited to dredging material within a couple or 3 kilometers of the dam. You can go further with fine material, less distance with sands, because sands require higher velocity to prevent the deposition within the pipeline. This shows a photo of the 700 millimeter diameter dredge at Valdesia Dam in the Dominican Republic. This is no longer in operation, but it just gives you an idea what it looks like. You see the pipeline is submerged, and here's the outlet, the downstream face of the dam, and this is the head that they have available to work with between the top of the dam and the outlet. Dredging is high energy intensive, high cost. It's not sustainable in the long term if disposal sites are limited, and the environmental impacts are quite variable. Flushing is another option, and with flushing, what you're doing is opening a lower level outlet to allow the water to run through the length of the reservoir and flush out a flushing channel. This generates high sediment loads downstream, Some places you can do it, a lot of others you can't. In this particular reservoir, I want you to look and notice that the power intake is not adjacent to the bottom outlet. And if we look at the aerial photograph, you'll see the bottom outlet here was placed on the right-hand side of the dam. Easily could have been placed on the left hand when they did the drawings, and they did the original design. And the intake could have been extended so that when they opened the outlet for flushing, that the channel would have cleaned the intake. As it is, they have to empty the reservoir to clean the intake. So this is just an idea of an example of the type of forward thinking, looking into the future, how we're going to handle sediment that could have essentially a almost no cost change to the design that would have made it life much, much easier for today's operators. Flushing limitations, you have to completely empty the reservoir. It's only useful for hydrologically small reservoirs that could be emptied. In other words, you're not going to capture all the water. You have to have water available to flush sediment. The flushing channel is typically not wider than the original river channel. So you're not going to move a lot of sediment from wide reservoirs. And when you try and release a lot of sediment in a short period of time, you can have potentially significant impacts downstream. You can have concentrations that easily exceed 100,000 milligrams per liter. Here you see a diagram showing the reservoir sediments, the flushing channel, and the flushing channel is what you can sustain through flushing, this volume of water, but the submerged floodplain, when you fill the reservoir, this area will continue to accumulate sediment, but at a much, much lower rate, because remember, your turbidity currents will run into the flushing channel, so most of your sediment will continue to be sedimented here, and your sedimentation rate on these off-channel areas will be greatly reduced. This is Kaligandaki back in Nepal again. This showing you that when this dam was emptied, the flushing process does not clear the entire width of the reservoir. Even though this is a rather narrow reservoir, notice it goes around the corner here, and it doesn't clean out everything. So flushing has a lot of limitations. It can be very useful, particularly for hydropower reservoirs in mountainous areas, but it's not an answer to all the problems. And the downstream impacts can be quite significant. This is at Kachina Reservoir in in Costa Rica, showing that the bottom intake is right next to the flushing channel. This allows turbidity currents to flow down the flushing channel and through the turbines. They release over 20% of the annual sediment load as turbidity currents that goes through the turbines of this particular plant. Downstream during flushing, what you get is a spike, a very high spike in your sediment concentration, which drops off quite rapidly. And at some point, in this case, they typically flush for about 3 days. There's not much more sediment being removed. You close the outlet and refill the reservoir. This high spike and these high concentrations are the critical environmental issues for flushing. And to minimize these downstream impacts, you need to look at diluting flushing releases, avoid biologically critical periods, more frequent flushings rather than less frequent, because you're removing less material every time, and you release clear water following a flushing event to help clean the river channel below the dam. And if you can keep oxygen in the low of the hypolimnium of the reservoir before the flushing, this also can help remove some of the oxygen stress. Finally, we're going to look at some adaptive strategies. Now, an adaptive strategy is basically an action that doesn't reduce the rate of sedimentation. And there are 6 basic strategies. You can optimize available storage, you can focus sedimentation, adapt to sediment encroachment, increase storage, reduce the demand for reservoir services, basically demand for water or power, or decommission the project. So when we look at optimum use of available storage, you have to think that many reservoirs have operating rules that are now close to 50 years old. Can that operating rule be modified to better match today's needs and technology? You can reallocate the storage to higher priority uses. Shared pools. Your conservation pool can encroach into a flood control pool when flood hazards are minimal. You do this based on real-time hydrology. Use real-time hydrology to optimize management of a shrinking flood control pool. When you know what's coming in from upstream, it gives you a better opportunity to optimize reservoir management. And the conjunctive use of your available storage with other sources of supply, including both surface and groundwater. You want to manage a water system as opposed to simply managing each component as a compartment. Sediment focusing. What you're typically trying to do when you focus sediment is to focus it upstream. Why? Because the delta contains coarse sediment, and with the coarse sediment reaches your intake and gets into your power turbines or your irrigation intake or whatever other element you have, it's typically going to create lots of problems. Now, on the left-hand side, we have a reservoir, this is Chivor in Colombia, showing the operation levels that have been unchanged for about 36 years. And you'll notice that the sediment is moving towards the dam. The delta does not grow vertically very much. On the right-hand side, we have a reservoir which has been managed to focus sediment upstream. This is Tarbelan, the Indus River in Pakistan. The initial water level, the initial minimum operating level, and the current minimum operating level. It goes up a couple of feet every couple of years. So over 38 years, look at what happened to the top elevation of this delta. What they have done and what they continue to do is raise your minimum operating level to focus the sediment upstream to keep it away from the power intakes. This is a photograph of Chivor showing the upstream, the very upstream portion. You can see when they draw the reservoir down on the annual drawdown, all the sediment gets scoured from the top of the delta and moved downstream. So as you operate the reservoir, you're moving these delta sediments closer and closer to the dam. So by gradually increasing the minimum operating level, you can keep them away from the dam. This is only a slowdown technique. It doesn't reduce the rate of sediment deposition in the reservoir, but it'll help put the problem, avoid the problem in as long as possible. A fourth option is to increase the storage volume that's been sedimented. You can raise a dam, you can build a new sustainable reservoir somewhere else, one or more reservoirs, or another very interesting option is you can use groundwater storage. Groundwater, of course, has the advantage is not subject to sedimentation, and by operating a reservoir conjunctively with groundwater systems, you can generate a lot of benefits. Encourage recharge of groundwater systems, and the sedimenting reservoir may itself be able to capture and divert spills to recharge. For instance, we have a project we're doing like this in Puerto Rico right now. Patillas Dam, built in 1914, has been losing volume to sedimentation, but a couple of years ago, they also lost a significant amount of volume because of a forced drawdown for dam safety issues. This is a hydraulic fill dam, and they have to lower the level for dam safety. So this reservoir is rather small compared to the runoff. It's discharging 60% of its annual average inflow to the dam, to the sea. So you're spilling a lot of water, and your firm yield users are 2 different municipalities, and you have irrigators and a couple of industries. But there's also another municipality, Salinas, that relies entirely on wells and has a very severe aquifer depletion problem. So in this particular case, what we're doing, instead of trying to take water from the reservoir and sending it directly to Salinas through a new filter plant, which would basically take firm yield away from the existing users, which are completely using the available yield, what we'll do is take water from the reservoir and use it to recharge the aquifer in the area of the Salinas well field. Basically, the top 5% of the operating pool will be designated as a recharge pool. And once the water level goes into this recharge pool, water will be delivered to the recharge system. This is an additional extraction from the reservoir, in addition to the normal rate of withdrawal. When the water level drops back down into the conservation pool, there's no recharge. And by doing this, we're able to produce, deliver approximately double the amount of water that's used by municipal users in Salinas. 5, reduce demand on the reservoir. Typically, you can think of declining firm yields. You can look at water conservation by users. They may be urban users, they may be agricultural users. You can think in terms of what is cheaper. Is it more cost effective for me to do water conservation or to try and build a new project or recover capacity, dredging a reservoir, etc. Transfer by water rights from lower priority users, plan for the eventual loss of reservoir benefits up to the point at which you have a planned long-term capacity that you can sustain. So think long terms and how you can reduce the demand and bring the demand down to what you can sustain on a long-term basis. Some types of benefits, though, may simply be lost. And finally, decommission the project. Decommissioning may involve dam removal, may not involve dam removal. This particular photo is the Elwha River restoration of Washington State, a project which the Bureau was heavily involved with. And it just gives you an idea of the sediment deposits, which were not particularly large in this reservoir, but they were and continue to be in the process of being eroded and carried downstream. Of course, if you have a large amount of sediment in the reservoir, if the reservoir fails because of sedimentation, the sediment load and what to do with that becomes a potentially intractable problem. So a few closing comments. First of all, think long term. What are the consequences of decommissioning? If you can't manage sediment, what's going to happen? Are you going to have to decommission, remove the dam, keep the dam with all the sediments? Think about that, because that will probably have some relevance on how you manage this particular reservoir. A variety of management techniques are available. We discussed very briefly several of them. The best strategy will typically involve use of more than one technique. They may be used simultaneously, or some techniques may be used first and others used later as sedimentation becomes more advanced. Plan and design for the sediment management techniques that will be needed in the future. So, for instance, if you are going to employ one technique now, but you know that you're going to be needing to use a second technique, say 50 years in the future, think about that future requirement and plan your infrastructure modifications so that they help support future management rather than work against it. And finally, monitoring is required to determine how to optimize management. Free technical resources, look at the website reservoirsedimentation.com and you can get a copy of the Reservoir Sedimentation Handbook, download, it's for free. The Extending Life of Reservoirs, World Bank publication that George and myself and Pravin Karki put together in 2016, that's available also for free. You can Google search Extending the Life of Reservoirs and it'll take you right to the World Bank page and you can download it from there if you want also. So thank you very much for this opportunity to say a few words about sedimentation, and we'll break for questions.
Great, thanks, Greg. So I think what we'll do is just go straight into these questions, if that's okay with you.
Sure.
So the first question we have relates to off-channel diversions. The question is there sufficient sediment transport capacity downstream from an off-channel diversion to keep the sediment moving? And my interpretation of that would be in the actual river channel, between the river channel and the reservoir. Or
Yes.
sorry, river channel and downstream of the
that is not a problem. Typically what happens is that the off-stream diversions are diverting your moderate flows, whereas the largest part of the sediment is discharged during large events. Now, what happens is that in some rivers, the Rio Grande, for instance, there are multiple diversions, and you're basically draining all the water out of the river, and you end up with insufficient water to transport sediment. But typically, where you would use an off-stream reservoir in a moist climate, that is not typically an issue. And if you have, for instance, the Western US, where you have a climate where these storms are more episodic, the off-stream reservoir will be less appropriate from the hydrologic standpoint, simply because you end up having a very, very large diversion line into the reservoir, and you're trying to divert so much water that you're going to take so much sediment with it that it doesn't make any sense. So the off-stream reservoirs are quite dependent on the hydrology, and where they work good, the sediment tends not to be an issue.
Okay, great, thank you. Okay, so the second question, in the US, we are not going to build more dams. How can we make what we have last longer and make them more sustainable? For example, if we implemented sustainable sediment management everywhere tomorrow, would we just reduce the rate of volume loss?
I
know that's a big question.
There are a variety of processes that can be used for converting today's dams into sustainable resources. Some of them are quite expensive, dredging, for instance. Fortunately, in the United States, the sedimentation problem here is not severe at this time. And we have a lot of reservoirs, particularly the federal reservoirs, which are hydrologically large, and we're not going to see a big problem for quite a while yet. But there are areas that are seeing problem today, and they're finding solutions which aren't convenient because they are expensive, but solutions do exist, and some of them may involve building a new reservoir, some of them, and there is some reservoir construction going on, some of them may involve dredging, some of them may involve other types of processes. So California, for instance, is working a lot in the area of recharging their groundwater system. And in the long term, that may be a very interesting contribution of water supply storage in that area of the world. So the techniques are available. They're not cheap. They're not easy, but it's doable.
Okay, thank you. Okay, so this next one is I think kind of a general question regarding the United States. The question is, as an experienced practitioner, what do you feel is the most practical scenario for maintaining US reservoir uses for the long term? And I was interpreting that to mean probably not just engineering solutions, but also sort of a big scale solution to the problem.
I don't see a single silver bullet solution out there. It depends a lot on which part of the country you're in and what particular types of problems you're looking at. For instance, when we look at the Missouri River, sediment sluicing at Gavin's Point, for instance, was something we've looked at and seems very feasible. Some of the other reservoirs you may end up dredging. Some of them you may actually end up losing. There is no single solution that we can say nationwide, because you compare the East Coast versus the West Coast, you compare flood control reservoir versus conservation versus hydropower. Hydropower has a lot more options available than, say, water supply, because hydropower is less sensitive to storage loss than water supply, firm yield. Hydropower, we're seeing the hydropower industry going more and more to occupy the role of a peaking power supply in complementary to the interruptible renewables like solar and wind. So hydropower becomes less important as a seasonal supply of power and more important as a peaking power source. And to maintain a peaking power pool, which is relatively small, is much easier than, say, trying to maintain a very large seasonal storage pool. So again, it depends. It's very site-specific, very hydrologically specific, West Coast, East Coast, middle of the country. And there's a lot of options, and all of the options we talked about today will be used at many places in the country. There's places for all of them.
Mm-hmm. Okay, thank you. Okay, so the next question regards partly a comment, I think, from the first few slides. If you mind heading over that to your first few slides. The question is the initial hydropower example for carryover storage or run of the river? The first example shown for water supply also applies to storage hydropower, and there might not be any difference.
Okay.
I think we have one of these.
Let me show you the two of them. This first, I don't know if you're seeing this. Are you seeing this? Are you seeing the screen?
Yes,
Yes.
I see it.
Sorry.
Okay. These are storage yield curves for firm yield for a water supply reservoir. And this is pretty standard, straightforward. You generate these curves from an inflow hydrograph, and this may or may not have carryover storage. This particular one shows live storage from 0 out to 1 year of mean annual storage. This is conceptual. These aren't actual numbers from a particular reservoir, but they're pretty close to some stuff that I've worked with. But now when you go to hydropower, here we've got across the bottom scale, live volume is percent of annual inflow. So we've got 50% of annual inflow. This particular reservoir is initially sized at 40% of mean annual inflow. And the firm dry season supply reacts quite similar to the firm yield for a water supply reservoir. This is only showing firm dry season energy because this is a monsoon climate. During the 3 months of monsoon, you have a lot of energy available from run-of-river projects, so you don't need to use your storage project. You use that water to refill the reservoir because the monsoons, if it's a bad monsoon, very weak monsoon, you may not be able to fill the reservoir if you're producing power during the monsoon at the storage site. So, but the firm dry season energy is very similar to what you would see for a firm yield for water supply. The dry season total energy is a little higher because you're operating the reservoir to capture and run through your turbines additional flow that you get during a wet dry season. The total annual energy, though, is fairly flat. your run-of-river would be here at about 0% capacity, and run-of-river at this particular site is around 1,100 gigawatt hours per year. So because the turbines are sized rather large, they can typically process, convert to power most of the water that comes through during the monsoon. And that's why your total annual energy doesn't decrease very much, even though your firm energy decreases dramatically. And this is not atypical of many hydropower projects that I've seen, because hydro turbines are sized so they can produce power, energy for power peaking. So you would design the project so you could produce a lot of energy during your peak hours, and you may shut it off during the non-peak hours. And as a result, we have this difference between the behavior of your firm energy versus your total energy. And that's why the total energy curve for hydropower project doesn't decrease very much.
Okay, thank you. The next question is, most of the examples shown in the talk have sediment getting very close to infrastructure. Presumably even sediment causing small fractions of change in total capacity would cause issues too. Could you comment on this?
Say that one more time. I didn't hear it very well.
Sure, yeah. Most of the examples shown in the talk have sediment getting very close to infrastructure. Presumably even sediment causing small fractions of change in total capacity would cause issues too. So I'm guessing mostly they're talking about water supply potentially. Yeah. Could you comment on this?
Some reservoirs have experienced problems with a relatively small percentage of volume loss, 5, 10, 15% volume loss, in part because in some cases, turbidity currents will carry sediment into areas that they maybe hadn't anticipated. And in other cases, the reservoir, when it's drawn down, in other reservoirs which are nearly emptied every year, in those cases, you will have the opportunity for even small amounts of sediment to be carried into the area of intakes. Low-level intakes, very, annual drawdown, almost to empty, for instance, for power production or irrigation. So it depends on how the reservoir is operated. If the reservoir is normally maintained at a high level, for instance, a water supply reservoir in a moist climate that is drawn down only occasionally, then you would probably not experience that type of problem very early. But if you've lost 50% of your capacity, regardless of where you are, by that time, you're probably looking at problems.
Okay, thank you. Okay, so the next couple of questions, I'm going to try to combine them here. They deal with sediment that is discharged downstream, so either by dredging or flushing. The question is, won't there be environmental issues affecting fish habitat, that sort of things? There's a couple of comments about effects on physical habitat for native species in the Colorado River in Grand Canyon. Yeah, so I don't know if you could comment about that. I know that's definitely an issue here in the States, maybe less so in other countries.
Yes, the discharge of sediment downstream, ideally we would be able to have the reservoir be essentially invisible from the standpoint of sediment. Unfortunately, what happens is that the fine sediment, which is not typically what we want from the environmental standpoint in the river downstream of the dam, is a lot easier to move downstream than the coarse sediment. When you build the dam, you cut off this coarse sediment supply, you end up with degradation of your bed downstream, you end up with coarsening of the bed downstream, you end up with a more simplified channel, a lot of environmental impacts associated with dam construction. And unfortunately, it's difficult to take these materials that are coarse grained and move them downstream because they deposit where? In the delta upstream. So any way that we could get the coarse materials downstream would generally be welcome. But moving anything downstream into an environment which has maybe had 40 or 50 or 60 years of essentially sediment-free environment is going to cause some pretty dramatic changes. And this is an issue, obviously not just in the United States, but all over the world. It's in most countries it is an issue. One of the things that when you address this that you probably need to consider is that when you look at the impacts downstream, you need to look at the river upstream of the reservoir versus the river downstream of the reservoir, rather than looking at the river downstream of the reservoir pre and post sediment release, because your pre-sediment release situation is entirely artificial. It's a sediment-free environment created by the presence of the dam, and it's only a temporary condition because the dam will eventually fill with sediment, and that once filled, the sediment will again start moving downstream.
Okay, thanks. Tim, do you want to comment here about the NRSST position paper?
Yes, we'll try and point out some of these things. I think Greg has made a great answer. A lot of it has to do with whether you're talking native species or introduced species. There are a lot of sport fisheries in the tailwaters below dams, and I'm sure those anglers are very avid about their sport fisheries. And as Greg pointed out, that sediment-free condition cannot last forever. The idea that all owners of dams and reservoirs will be required to trap sediment forever is really a fantasy, and that sediment will have to come down sometime.
Okay, thanks. I was thinking more along the lines of what the general gist was of the position paper, just to try to get better permitting and to allow sediment pass through. I don't know if you want to comment about that, Tim.
Well, okay. The Subcommittee on Sedimentation has proposed a position paper on permitting so that there is a path forward. Sometimes the permitting process can be quite difficult, and all sediments are treated as pollutants, but in reality, not all sediments are contaminated. So since allowing the sediment downstream is a natural process, we are pushing this position paper to try and make the permitting process more tractable.
All right, thanks, Tim. Sorry to put you on the spot there. So we have a few different questions that are in here that I think I'm just going to, I'm just in the interest of time, going to skip over. One of the other questions that came up is regarding climate change and sediment yields. So the question is, do you have any approach regarding live volume storage and sediment yield, considering climate change in the USA or Latin America or any other region? How climate change could favor a reduction in sediment yield?
How can climate change favor a reduction in?
Yeah, I mean, that's what the question said. I think the main question would just be, how would we help to factor in sediment yield in the case of climate change? I mean, presumably some of the places sediment yield will be reduced, some places sediment yield will be increased. So do you have any comment just about climate change and sediment yields in general and how to factor it in?
Basically, it depends on where you are. For instance, I've seen studies in the Midwest that they ran models, farm models, looked at how the cropping would change. But as the cropping changes, your erosion control procedures also change. So it's not like you're going to have this change in climate and all of a sudden everything else is going to remain the same. The climate changes, but your land users are going to respond to that. Now, having said that, the anticipation that we'll have more severe storms will tend to increase sediment yield. But probably the biggest impact would be the change in land use. For instance, we're seeing in the western United States a lot of fire activity. I was a couple of years ago, or 3 or 4 years ago, going through Rocky Mountain Park in Colorado. And you see the beetle infestations, you see the dead trees, you see an environment which is ready for fire. And is this climate change is presumably one of the driving functions on this, the increasing dryness, changes in climate. But what really will trigger this is that the forest becomes weakened, the trees begin to die, you have a lot of dead standing wood, a lot of fuel, and then you have your catastrophic fire, and then you have your post-fire condition, which generates high sediment yields.
Okay, thanks, Greg. So one last question here, and then I think we can wrap up. This is a question just about sediment monitoring. So the question is, some of your sedimentation management measures rely on accurate knowledge of sedimentation inflows. In the US, do we have enough sediment gauge data? What is the minimum that we need? I know that's a hard question.
In the US, we don't have enough sediment gauge data, and we also do not have enough monitoring data of the sediment process in reservoirs. The minimum that you use, it really depends on what type of strategy you're going to use. If you're going to be dredging, you probably don't need an upstream gauge. If you're going to be doing something like sediment sluicing, it's going to require quite a bit of data to design that process properly.
Mm-hmm. Yeah, this might be a good question to talk about a little bit for the monitoring talk.
I'll write that one down.
Yeah. Okay, great. Well, thanks, Greg, so much for giving this talk. And thanks to all the attendees who have stuck it in there, stuck it out with us. Well, Greg, thanks so much. And I guess we'll get in touch with you about sort of getting this all edited. Tim, do you want to say any closing words?
Just thank you very much for a great presentation, Greg, and Toby. Thank you so much for moderating this session and facilitating all the logistics.
Well, thank you, gentlemen, for sponsoring it and for inviting me.
Sounds great. All right. Thanks, Greg. We appreciate it.
Okay.
All right. Take care.
Good afternoon.